Okay, our last example of partial fraction decomposition is a very long and challenging one. First of all, notice the top is degree 4. The bottom, if I were to expand this out, this will be degree 4, this will be degree 1, so it's degree 5 if I were to expand it out, which you don't want to do, but the degree of the top is less than the degree of the bottom. So no polynomial long division, at least, needed. We have already factored the denominator for you, thank goodness. And you can see there is a irreducible quadratic factor x squared plus 1 that appears twice, right? It's x squared plus 1 times x squared plus 1. So we're going to have two fractions in our partial fraction decomposition from this. And then there's a linear factor as well, x plus 3. There'll be one fraction there. Okay, so let me step you through this process. I've already written out the solution, so I'm just going to go through it step by step. And we're going to start with the fact that we have a linear factor here, x plus 3. There's only one of them, and so I have constant over that linear factor. Quadratic factor, I've got two of them. The first one, x squared plus 1, I'm going to have a linear factor above, bx plus c, and then x squared plus 1 squared, linear factor again, dx plus e. So remember, for all these quadratic factors, we have a linear factor up top, and I have one for each power here, right? If it was cubed up here, we would have a third one, right, which would be, I don't know, fx plus g over x squared plus 1 quantity cubed. Okay, but we stop there. Okay, so now what I'm going to do is I want to find the values of a, b, c, d, and e. So the first thing is I'm going to multiply by the least common denominator, which is this denominator here. When I do so, I get this. Let's see if this makes sense. So obviously I get the numerator here by multiplying by this denominator. This denominator times this, the x plus 3 cancels, and I'm left with a times x squared plus 1 quantity squared. Here, one of the x squared plus 1's cancel, and so I'm left with x squared plus 1 times x plus 3. And then here, the x plus 1 quantity squared cancels, and I'm just left with dx plus e times, it's down here, x plus 3. Okay. All right. Now, how can we find the values of a, b, c, d, and e? Well, first of all, I noticed that I can use this linear factor, the shortcut, and say, what if x is negative 3? I know I can't use it up here, but I can use it here if I plug in x is negative 3 into this polynomial. All right. Over here, notice this goes to 0 and this goes to 0. So these two terms are 0, and I just have what a times negative 3 squared plus 1 all quantity squared. So if I clean this up, this gives me 9 plus 1 is 10. 10 squared over here, which is 100a. All this, if you evaluate it, becomes just 400, and so you get a is 4. So I've got one of my unknown quantities, a. I still have b, c, d, and e. I don't have any other linear factors to do that shortcut with, so I'm going to have to proceed with the method of undetermined coefficients. Okay. So if I go ahead and let a now be 4, I'm going to square x squared plus 1, which gives me x to the 4th plus 2x squared plus 1. Make sure you know how to do that. And then I'm going to FOIL out a bunch of stuff over here. So this is going to be some work here. So I FOIL bx plus c times x plus 3. So I get the first times first is bx squared. The outer is 3bx. And the inner is cx. So 3bx plus cx is 3b plus cx. In other words, I've just combined those two like terms. And then the c times 3 is 3c. So I've expanded just this out. I still have times x squared plus 1, so I've got some more work to do here. Here I FOIL, I get dx times x is dx squared. The outer is 3dx, the inner is ex. 3dx plus ex is 3d plus ex. And last, e times 3 is 3e. Whew. Okay, still not done though. I'm going to do a little more here. I'm going to distribute the 4 through here, and I need to multiply each term here by x squared and then each term here by 1. Okay. So distributing the 4 gives me these 4 terms here, right? bx squared times x squared is bx to the 4th. 3b plus cx is going to be times x squared is going to be 3b plus c x cubed, right? Because I'm multiplying x times x squared. And then 3c times x squared is, I've lost it. Oh, 3cx squared. Okay. And then I also need to do bx squared times 1, 3b plus cx times 1, and 3c times 1. Okay. So that multiplies all that out. And then I have the dx, these I just copy down. Whew. Okay. Now I need a drink of water. Okay. So now we need to combine like terms. Do you see my two x to the fourth terms? I'm going to sort of cross them as I go. 4x to the fourth, bx to the fourth. That's 4 plus bx to the fourth. What about x cubed? Okay. Well, this is the only x cubed term I have. Okay, all the others, there's no x cubed. And then x squared. So I've got 8x squared plus bx squared, okay, and then plus 3cx squared, and then plus dx squared. So I've got 4 of those. I've got to add all those coefficients together. The x terms, then I've got 3b plus c, that's right here, and then 3d plus ex. And then the constant terms, what's left? 4 plus 3c plus 3e. Whew. All right. That was a lot of fun. Okay, so what have we done? After all that work, what are we doing? Don't forget that all this stuff here is equal to this original polynomial. So what do we know about the x to the fourth coefficients? 4 plus b must be equal to 3. 3b plus c must be what? Negative 3. 8 plus b plus 3c plus d must be 9. This stuff all has to be 4, and the constant term has to be 7. It's the method of undetermined coefficients. So I can now match up, and I get these 4 equations that I just stated. Okay. Now this one right away tells me what? 4b plus 3 tells me b is negative 1. Okay. If b is negative 1, now I can plug it into the second one. 3 times negative 1, get negative 3 plus c is negative 3. I get c must be 0. C must be 0. And notice that's possible. As I said, some of these can be 0, and that's the case. That's good. And now I can go here. I can let b be negative 1 and c is 0, and I can solve for d and get d is 2. And then again here, c I found is 0, so I can now plug that in and I can solve for e. E is 1. So a lot of times these systems are pretty big now. I got 4 equations here in 4 unknowns, but pretty easy to solve. Pretty easy to solve. Okay. So now I go back to my original partial fraction decomposition here. The a, the b, c, d, and e are here. So I'm going to take all these values. If you remember, I previously found a to be 4 right here. And I've got these values of b, c, d, and e. So I plug them all into this, right? And now the integral that I'm looking for is the integral of this. And so I'm going to do that right here. So a was 4, b was negative 1, that was bx, so negative 1x, and c was 0, so bx plus c is just negative x. Okay, and then d was 2, so I got 2x, and e was 1, 2x plus 1. And so here it is. So the antiderivative of 4 over x plus 3 we know is that. That's pretty easy. The next one's pretty easy too. If I let u be x squared plus 1, du is 2x dx. I've got a negative x dx, so multiply both sides by negative 1/2. So this is negative 1/2 du over u, which is negative 1/2 natural log absolute value of u, which is negative 1/2 natural log u was what? X squared plus 1, which is positive, so I can get rid of the absolute value bars. Okay, so the first two pretty easy. This one, if I let u be x squared plus 1, I get u squared in the bottom, but du would be just 2x. I've got a 2x plus 1. So I have to split this up like we did before, right? So this will be 2x over x squared plus 1 quantity squared plus 1 over x squared plus 1 quantity squared. Okay, just split that fraction up into 2. Now this one is a simple u substitution. Let u be x squared plus 1. Du is 2x dx. That's exactly what we have up top. I get du over u squared, which is what? Remember, this is the same as what? The integral of u to the negative 2 du, which the antiderivative is u to the negative 1 divided by negative 1, which is negative 1 over u. Okay, So it's not log. Notice it's just power rule. And u was what? X squared plus 1. Okay, so there's the antiderivative of that. All right, last I have this one. Well, this one is a big bear, because if I let u be x squared plus 1, du is 2x. I don't have a 2x up top. Okay, well, this last one can be done with trig substitution, which is a method we looked at prior to this lecture on partial fraction decomposition. And it's x squared plus 1, so I'm going to let x be tangent theta, if you remember that process. Dx is what? Secant squared theta d theta. And why did I choose x to be tangent theta? Well, because x squared plus 1 is then going to be tangent squared theta plus 1, since x is tangent theta. But tangent squared theta plus 1 is secant squared theta, and secant squared is secant to the fourth. So I'm able to rewrite that x squared plus 1 in terms of secant. And so up top, I get it's dx. Don't forget, this is dx is still there. So I've got so really this is looking at the integral of dx over x squared plus 1 all squared. Okay. So the dx, what's the dx? Secant squared theta d theta. X squared plus 1 squared is what? Secant to the fourth. Secant squared divided by secant to the fourth, we can cancel out a common secant squared. I left with d theta over secant squared theta. But what is 1 over secant squared theta? That's cosine squared theta. And this goes back to trig integrals now. So we showed a method for finding this by using the power reducing formula for cosine, which is cosine squared theta is 1/2 1 plus cosine 2 theta. And that, using a simple substitution, becomes 1/2 theta plus 1/4 sine of 2 theta. Okay. So you should have done this before, and if you haven't, do it again till you understand the process. But sine of 2 theta is 2 sine theta cosine theta. So 1/4 times 2 is 1/2 sine theta cosine theta. And that's the way I prefer to write it in this case. Notice I do need to get back to the variable x, right? I know x is tangent theta, but what is sine theta and cosine theta in terms of x? Since x is tangent theta, theta is what? Tangent inverse of x. So I know theta is tangent inverse of x. And so I do my right triangle here. You remember, I know that x is tangent theta, so tangent theta is x over 1. Remember, tangent is opposite over adjacent. Opposite over adjacent. So the opposite side is x, adjacent side is 1. And that leaves what? X squared plus 1 squared, x squared plus 1 square root. That's the hypotenuse by the Pythagorean identity. So sine is what? Opposite over hypotenuse, x over that. Cosine is adjacent over hypotenuse, 1 over that. And of course theta is equal to tangent inverse of x. So I've got 1/2 theta, which is tangent inverse of x, plus 1/2 sine of theta is over here, cosine of theta is over here. Multiply top is x, bottom is 2 times this is just 2 times the quantity x squared plus 1. There's our antiderivative. Woo! Finally. Okay, so what I have is, going back to what we had before up here, this was that 4 times the absolute value of natural log of x plus 3 plus negative 1/2 natural log of x squared plus 1. It's right there. Right? And then this one we split up into 2. This one was negative 1 over x squared plus 1. Right there, negative 1 over x squared plus 1. And then finally, the last part we found was 1/2 tangent inverse of x plus x over 2 times x squared plus 1. Okay. And there it is, right? And don't forget our plus c at the end. Whew. Okay, we're done. Now, one thing you might look, hey, we can do a little simplification. Notice this is x squared plus 1. This is 2 times x squared plus 1. So if I multiply top and bottom by 2, 2 over 2 times x squared plus 1, I get negative 2 plus x, or x minus 2 over 2 times x squared plus 1. So I just did that little simplification. And there's my antiderivative. Okay, there's my antiderivative. All right, and you can look in that textbook. There's a similar example to this if you like this, and in section 7.5 you might want to try it. So this is, the way real life is sometimes. You got a lot of stuff in here. This has partial fraction decomposition. This has trig substitution. It's got, our traditional, U substitution, power rule. It's got inverse tangent. It's got a little bit of everything, and it's exciting, and it's fun, and it's wild, and it's crazy, and that's what calculus is all about. So we are going to sort of wrap up now, in a sense, over the our different integration techniques. We'll talk about some strategies, some general strategies in some future lectures. We're going to take a little break and look at something known as improper integrals, and then we'll go back to summarizing these integration techniques. Okay, but again, very specialized techniques, but very helpful for certain types of functions and finding their antiderivatives. Partial fraction decomposition. I hope you enjoyed it.